is we're going to start marching our way through a long set of statistical techniques that people use in doing statistics, and we're going to start small and we're going to build up. You've already done some techniques, so chi-square are all kind of the simplest techniques because calculations are relatively uncomplicated. The idea is relatively uncomplicated. T-tests are kind of at that same level of sophistication. A lot of times people will use t-tests in inappropriate situations because they learned to use a t-test in some class that they took in the past, and they didn't learn anything beyond that, and so they fall back on what they know, even though it might not be appropriate. But t-tests are useful, especially if you are only dealing with one or a couple of samples that you are trying to compare with one another. So t-tests consist of three different types. You can have a single sample t-test, you can have a two sample t-test, and you can have what's called a paired t-test. In all of these things, you're basically using parameter estimates. So in this case, the parameter that you're comparing or the parameter that you're using is the sample mean. And so because you're using the sample mean, you're using the sample mean as a stand-in for the population mean. That means that this set of tests conforms to all of the expectations or all of the assumptions that you would have for any of the other standard parametric tests. What are the assumptions of standard parametric tests? Yeah.
Randomness.
So your data are collected randomly. What else? Somebody else. The data are independent. What else? What's that? They're representative. This kind of goes into how you go about collecting your data. Yep. What else? Well, clearly, if you have a one sample test, if you only have one sample that you're looking at, you can't compare variances to another sample because you don't have another sample. In the case of the single sample situation, in a single sample t-test, what you're doing is you're comparing a sample to some hypothetical value. And so let's say that you're a business person, you're studying organizational culture, you look at Japanese manufacturing plants and U.S. manufacturing plants, and you discover that one type of plant has way higher productivity than the other type of plant. You might then go and look at, a national statistic published by Japan that says, this is the average productivity of Japanese manufacturing plants. Then you might go and take a sample of U.S. plants and say, okay, if we look at U.S. plants, how do these plants compare to the stated average productivity of Japanese plants, for example? In which case, you're comparing U.S. manufacturing plants to some hypothetical average that is published in some government report coming from Japan. And so obviously you can't have equal variances because there's only one sample that you're looking at. So for the single sample test, all of these things would apply, but this one would not because you're only working with one sample. Two sample tests, though, this would apply as well as all the rest of these. In a paired t-test, what you're doing is you're taking subject 1 in a particular experimental setup, and you're testing it at time 1, And then at some other time, you're taking subject 1 and measuring it again, let's say at time 2. So let's say that you're interested in physical fitness and you have a study where you're trying to determine whether CrossFit actually does anybody any good. Have any of you ever done CrossFit? Did it do you any good?
A little bit.
A little bit. If you wanted to know how much, you could actually set up an experiment where you basically had subjects A, B, C, D, E, F, G, H, I, J, K. You took half of these, 1, 2, 3, 4, 5, 6. You took half of them, enrolled them in a CrossFit program for 6 weeks. Took the other half, sat them on the couch in front of the housewives of, what are some of the housewives programs? I mean, watch this crap. Housewives of Beverly Hills. Set them on the couch with the Housewives of Beverly Hills for 6 weeks. Before you did either of these things to them, you, for example, gave them a set of tests. Maybe you ran them in the 100-meter. So you could look at their speed in the 100-meter. Before, and you could look at their speed in the 100-meter after. And so you would have a speed for this individual before and after, this individual before and after, this individual before and after. Which of these assumptions does this data set violate? Somebody other than Karis. If before CrossFit I ran the 100-meter in, I don't know, what would I run the 100-meter in? Probably 3 days. What would a normal person run the 100-meter in? 15 seconds, okay. And then after 6 weeks of CrossFit, I ran it in 12, 18, I ran it in 14, et cetera, et cetera. The couch potatoes started out at 15 and ran it at 15 for person G. Which of these assumptions do these data violate? Oh my God, Karis. Which one? Independence. These are not independent. This data point is not independent of that data point. If somebody started out and could only run the 100 in 30 seconds, you would expect their time after CrossFit to be much higher than these other individuals simply because it started out way higher. And so these data points are no longer independent. Well, this is what a paired t-test does, is it allows you to relax this assumption that the data are independent. It actually will not look at the average of before and the average of after. It'll actually look at the difference between before and after and analyze that difference to see if that's usually significantly different from a difference of 0. So these are the 3 types of t-tests that you can do, and we will start marching through these as we go. If you downloaded this earlier in the semester, I got rid of that PowerPoint, and I've put a new PowerPoint on the Moodle site, so it's up there today because I'm taking a little bit of a different approach this semester to this than I did in the past. Questions about this so far? All right, so let's get to it then. A single sample t-test is when you basically have a sample that you want to compare to something else. So imagine that you work at a drug manufacturer and you have to demonstrate that your prescribed dose of the drug doesn't raise blood pressure more than 3 points. It's a stupid example. It's from a book because Generally, your blood pressure is measured as one blood pressure over another blood pressure. It's diastolic divided by systolic. And so I don't know what these points refer to, but whatever. This is an example pulled from a book. It can't change your blood pressure by more than this amount. It's the early phases of human testing, and so they don't give you very many humans to test on because they don't want you to kill anyone. That's always bad in drug development. So you give these people the drug, and then you measure how their blood pressure changed, and these are the data. Subject 1 changed by 1.7, subject 2 by 3.0, 0.8, 3.4, 2.7, and 2.1. So these are the data, and you're testing them against the hypothesis that these data are less than 3, basically. And so how do you go about doing this? Well, you have to calculate a t-statistic, the single sample t-statistic. Go online real quick and figure out what the single sample t-statistic is. Not from a table, but from the formula for how you would calculate the t-statistic. Should have a numerator where you compare your observed mean to some hypothetical mean. What's in the denominator? It's the standard error, isn't it? You should see something like this, right? Is that what you saw, or did you see it written out standard error? You saw both, okay. So it's simply the difference between the means divided by the standard error. You guys all know how to calculate the standard error, right?
So it's x bar minus mu.
Yep, so this is the sample mean minus the hypothetical mean. In this case, it's 3, yeah. Yep. Mu is the Greek symbol for the population mean. So another way of thinking about this is you're comparing your observed mean versus the population mean of 3, whatever that population is. So you guys know how to calculate standard error, right? Everybody know how to calculate standard error? Calculate standard error. Go. What's the first step for calculating standard error? Well, in order to find the squared variance, so the first thing you need to know is the sample mean. Yep. Once you have the sample mean, you can get the sums of the squares. Once you have the sums of the squares, you can calculate sample variance. Once you have sample variance, you can get standard deviation. Once you get standard deviation, you can get standard error. Get calculating. My math working out so far? Okay. This is what you guys get? Why have I been making you work through these problems by hand? Well, because the idea of the sums of squares and the idea of things like standard error come up over and over and over again as we go through doing other kinds of techniques. Looks like some of you are still working. So once you have the standard error and the mean, you have everything that you need to know. You know what the hypothetical value is that you're comparing to. You know what your observed mean is, and you know what the standard error is. So the t statistic is simply the observed value, the observed mean, minus the hypothetical value divided by the standard error. Notice how there are negatives on here. So when we subtract the hypothetical mean from the actual mean, because the actual mean is lower, that thing has a negative associated with it. So the t statistic that you get in the end is actually negative 1.848. And that's because you're comparing this to some hypothetical value. You're not comparing it to an average of 0 or something like that. So this test actually has directionality. You're testing to see whether or not this value is actually lower than 3. And you want it to be lower than 3 because this is what the FDA is telling you you need to have done. So since this is a directional test, are we going to be looking up key statistics in a t-table that correspond to a one-tailed test or a two-tailed test. It's a one-tailed test because there's directionality to it, which means that you can load all of your probability of a type 1 error into one end of the distribution of the t-statistic, which is nice because that gives you a better chance of finding a difference. So I did all the equations. I do a lot of this in Excel simply because it's easier to do math in Excel. I always calculate the sums of squares myself and then calculate the variance myself. And then you can always go through and you can use the formula in Excel, which is var.s, and then the range of the data to check yourself. And so I always do that. So this is me calculating it myself. This is the Excel calculating it. Same thing with sample standard deviation. You just take that and divide it by, take the square root of the variance, and that's what you get. This is when you type in this in Excel. Then you can get the standard error. There is, strangely enough, no formula in Excel for the standard error. Excel does not know what the standard error is because Excel is an idiot, because it's just a stupid program. And then the tcalc that I got was 1.848. So then the question is, well, what do you compare this to? So you need to go and get a t-table. And in this case, the t-table, I've chosen one that is a little easier for you to use because it has one-tailed probabilities and two-tailed probabilities at the top. Notice that for the one-tailed probability of 0.05, this leads to a value down here of 1.645. For the two-tailed probability of 0.05, where you have 2.5% out here and 2.5% out here in the t-distribution, that's 1.96. But since we're looking at just one side of the distribution, we want to know if our value is lower than 3. That's directional. We're going to be in this column because of this directional difference. So what's our sample size? Our sample size is 6. So how many degrees of freedom does that make? 5. So we come in this column down to 5, 2.015. But we put a negative in front of it because this is a negative difference that we're looking for. And so this is the t at alpha level equals 0.05, one-tailed, and degrees of freedom equals 5. Because the absolute value of this is larger than the absolute value of this, we would conclude that the sample is not different from an increase of 3 points. Yeah, and let me show you why that's the case. Remember that the t-distribution has a normalish sort of distribution, the t-statistic itself. At about 2 degrees of freedom, this includes 95% of all the t-values. At 3 standard deviations out, you have about 99% of the observations. So if you're testing to see if something could be larger or smaller, and you're testing at the 0.5 alpha level, 0.05 alpha level, a type 1 error rate of 5%, what you generally do is you put 2.5% of it out in this tail, and you put 2.5% of it out in this tail. And that's where your 5% goes, because you could see a t-statistic that is high this way or one that is high this way, depending on whether mean 1 is greater than mean 2, in which case you would be high over here, but if mean 1 was less than mean 2, you would be high over here. But in this case, what we're doing is we're making the hypothesis that we're expecting x1 to be less than x2, or at least that's the idea that we're testing, in which case this difference would turn out to be negative. And so we don't really care about whether that difference is positive at all. We want to know, is our sample less than the hypothesized value? So we take all of that 5% and we stick it down here. Well, the only reason that we would say that our sample is lower than 3 is if it generates a t-statistic that is further away from a t-statistic of 0. So we observed a t-statistic of 1.848, but for us to conclude that our sample is different from a value of 3, we would have had to have observed, for us to determine, I was saying it right the first time. We observed 1.848 negative, but for us to conclude that this was different from a value of 3, we would have had to have observed something greater than, what did we say? 2.015. So the rejection region out here is actually 2.015. So because we were inside of this, we're basically concluding that this could have been from a sample, from a population of 3. We would have had to have observed something that was outside of this range if we're going to say that ours is actually less than it. So to be absolutely correct, you would put the negative on there, and then you would look at this side of the table. But you could also just take the absolute value of the t and compare it to the positive side of the table. It doesn't really matter. But because we're making the test of whether or not what we observe is less than the hypothetical value, it's useful to keep the sign on there so that you know that your sample wasn't higher. Because in this case, if your sample is higher than 3, if this was a plus 1.848, then you've messed up. You're in the wrong direction altogether. The sign on that value is just the wrong direction. Yeah.
So does it matter whether we're looking for whether it reaches a 3% increase in blood pressure?
Yeah, they want it to be less than. So since this is not different from, it's actually not less than. It's equivalently equal to. And so this would be a concern. You would be hoping for a significant result because you want it to be less than.
Okay, I get it. So if you wanted us to answer a question like this, how would we answer this via analysis? Or via just we got our statistic, now
Yep.
we want to save our answer?
Oh yeah, because I didn't write out the rest of the answer. The sample is not different from an increase of 3. So it's not less than 3. It's approximately 3. This is indistinguishable from an increase in 3, is what it's saying. It's lower, the numerical value is lower, but statistically we can't distinguish this increase in blood pressure from an increase in blood pressure of 3. Now, if the FDA is saying, well, it has to be lower than 3, this doesn't meet that criteria because this is indistinguishable from 3. Okay? So In the same way, though, it's also not higher than 3. It's just indistinguishable from 3.
Okay, so what if you would have got 2.016? So it's bigger than.
So it's a decrease. It's less than 3 in that case. In which case you would be good. You would be marginally good. You would be on the very edge of good. But if you were a pharmaceutical exec, you would be like, all good, until you get more data and find that maybe 6 subjects wasn't a very representative sample. But yeah, if you were doing this, trying to get permission to add more human subjects to your trial, at that point, if you saw a t of minus 2.016, you could make the argument saying, we crossed the threshold, so we're good to go. Give us more humans to experiment on, and we'll get you a better answer. But this is the weird thing about statistical significance. If your observed t statistic was really minus 2.016, if we blew up this section, where this is the rejection region, you're basically, this is the border, this is the threshold, and you're right there. And so, I don't know, as a scientist, as a person who thinks about data, before I went asking for more humans, if this increase in blood pressure of 3 points on the blood pressure scale really was important, I might not want to go forward with this because you're just right there on the threshold of significance. And that's the tricky thing about statistical significance, is it's all arbitrary. Because I could have said, well, this is a preliminary data study with a really small sample size. I'm basically getting this data to see if I can proceed with testing on humans. So I may want to actually relax my type 1 error rate. I might want to say, well, I don't want to test at an alpha level of 0.05. I want to test at an alpha level of 0.01 because that allows me to see this difference if it's really there. Now, I might say that there's a difference there when there isn't a difference, but this allows me to see a difference a little easier. So what we would do there is we would go to this column of the table, go down to 6, and we would see that the t statistic there is 1.44. Did I say? Yeah. Oh, no, the sample size of 5, rather. 1.533. Sorry, sample size of 6, degrees of freedom of 5, which is 1.476. Negative 1.476. Now, this is further out than this is, and so we can say, yeah, it's less than 3. Give me more humans. Somebody emailed me after the test asking about the interpretation. I don't remember who it was, but the answer to your question is, when I'm asking for interpretation, this is what I'm asking for. The question is, in order to proceed with this study, I need my increase in blood pressure to be less than 3. If I test it at this level, it is significantly less than 3. If I test it at this level, it's not significantly less than 3. The difference between those two answers is, 1, what I observe is not different from 3, which means it's not less than 3. So in the eyes of the FDA, I would not be able to proceed with my testing at this other alpha level where I relax my type 1 error rate. Remember that the type 1 error rate is saying that two things are different when they're actually not. So I'm risking finding that the increase in blood pressure was low when in actuality it raised blood pressure. But once again, we have really tiny sample sizes. And so I'm not trying to present that you can just make the alpha level, whatever alpha level you want to make. But if maybe a 3-point increase in blood pressure is really physiologically not a huge change, it doesn't represent a huge risk to patients, then one could argue, once again, to the reviewers of the paper that this was not a big enough change, and so I can test at this other level and say, okay, we're good, pending more data. And when we have more data, we might actually tighten down the type 1 error rate again, simply because we have more data. The instructions in the textbook that I pulled this example from, they told the student to test at an alpha level of 0.1, not an alpha level of 0.05. 0.05 is just kind of standard practice, but there are all kinds of examples you can find where it's either made more stringent or relaxed a little bit. In all cases, let's say that you're writing something up for publication. In all cases, you have to generally justify deviating from an alpha level of 0.05. But if you do, you generally have to explain a lot more when you relax your type 1 error rate than when you make it more stringent. Because they want to know, well, why are you risking making the mistake of saying two things are different when they're not? And then you have to explain what that is. Nobody's really going to complain if you're making life harder on yourself, but they're going to ask a lot of questions if you're making life easier on yourself in terms of statistical testing. And so you have to have a pretty good justification for when you do this. There will be times, depending on the field that you're in, where you may get something back from a reviewer that basically says, we want you to test at a more stringent alpha level because the consequence of making a type 1 error is more catastrophic. You guys remember well, no, you probably don't remember. You guys weren't born yet. Jesus. Okay, I'm old. I'm officially old. The first space shuttle that blew up on takeoff.
Challenger?
Was it the Challenger? I don't remember if it was the Challenger. I guess it was.
That was the famous one.
Yeah, that's the one that blew up. The other one tore apart on re-entry. Yeah, so the Challenger goes up, gets partway to space, and then just explodes on live television, scarred a generation of little kids, because of course there was a school teacher on board. Do you remember what the cause of that catastrophic disaster was?
Was it like a little rubber tube that didn't hold up?
An O-ring, a rubber O-ring. So a rubber O-ring is just a circular piece of rubber that has a cylindrical profile when you take a cross-section through it. And it got cold the night before. It launched from Florida. Florida doesn't get very cold very often. And they tested those O-rings at what they thought were reasonable kinds of temperatures. Excuse me. One of the things that happens with rubber is when it gets cold, it gets brittle. And when it gets cold, it shrinks. And so someplace, somewhere, somebody tested these O-rings to see how much they shrank at what temperatures and how brittle they got at what temperatures. And they probably tested against some hypothetical shrinkage and hypothetical brittleness at a particular temperature. So you're a material scientist and you're working at NASA or whatever aerospace company did this work, and you're saying, okay, well, what's the amount of shrinkage that we can tolerate, at which point this O-ring no longer does its job of making a seal that keeps the fuel in the fuel tank versus letting the fuel leak out and the thing go boom. So what's that shrinkage? Well, it's a shrinkage of maybe minus 2% at 32 degrees Fahrenheit. And so what he does is he takes a bunch of these O-rings that the manufacturer has given him, and he cools them down to 32 degrees, and he looks to see how much shrinkage there is. And maybe he finds that the shrinkage is actually a shrinkage of negative 3%, and he's testing at an alpha level of 0.05. But because this is a material, it's not going to vary a lot, so that 1% actually has a really narrow variance around it. But he doesn't find that that's significantly different from that. And so he's like, well, we're good to go. 3% was not significantly different from 2%. We're good to go. This is the tolerance I was given. I gathered data. I found no significant difference. So now you put this thing out on the pad in the space shuttle, and it gets down to 28 degrees. What do I want to do percentages? 28 degrees Fahrenheit. And at 28 degrees Fahrenheit, which they didn't test at, this might have been 4%, which is now further away from the 2%, the minus 2% of shrinkage, and now is big enough that fuel starts leaking. And maybe you would have detected this 4% versus 2% difference if you had tested at a more stringent alpha level. If you had, maybe you would have found at this alpha level that this is actually different from that, and you better go back and redesign those O-rings. Situation where the type 1 error rate, the error rate of saying these two things are different when they're not, is actually really pretty important. Because if you say they're not different when they actually are, a space shuttle blows up. So a lot of times people in statistics, and I've never actually talked about type 1 error rate in quite this way, we talk about it as if, some people cover it as if 0.05 is the holy grail. You must have 0.05. Then there's another group of people who are like, it's flexible, it's arbitrary, just do what you want. But in reality, it's crucially important because you should make a type 1 error rate that you're testing at, the alpha level, you should make it appropriate to your question, appropriate to your data set, and appropriate to the consequences of making this particular type of mistake. I don't know who did the testing on those O-rings. I'm guessing they're probably not big fans of an alpha level of 0.05. I think they had, 6 or 8 astronauts? One of them was a public school teacher. Because there was a public school teacher on that particular flight, hundreds of thousands of school kids in elementary schools all over the United States were tuned in on their TV to basically watch this thing explode in the upper atmosphere. Alpha level is important. And sometimes alpha level isn't that important, but that's one of those cases where the level at which you're testing the tolerances of something become important after the fact. So as a researcher on this particular question about blood pressure, you would have to take your medical knowledge, your physiological knowledge, and say, okay, is 3 points upward on blood pressure, is that really something that is going to have serious health consequences or not? And then you could either relax your alpha level if it's not that big of a deal. You can leave your alpha level the way it was. Or if it is a big a deal, you might actually want to make the alpha level more stringent, making it even harder to detect that your drug doesn't get up to that 3 points increase. Sorry, Blaine. Was that a question? Was I answering a question that you asked? Because it seems like it was 20 minutes ago that you asked the question, and now I'm getting to the end of the answer.
You start like you answered that question and then kind of rolled it to a bigger
Okay. All right. Okay. Sometimes I just start thinking about things in my own head. I'm like, okay, well, you guys need to be able to think about this in these sorts of ways, and so.
So to that point, though,
Yeah.
you still just want to test on alpha level.
Unless I tell you otherwise. Yep. Yeah, and if you ever go off and do this for real, um, you're going to need a lot more training in applied statistics than what you're going to be getting in this class. And you will develop over time your own nuanced understanding of how all of this works. Uh, I was talking to some people from Texas Parks and Wildlife last week, and they asked me how I would do something. And the answer that I gave them was not really what they wanted to hear, because they just wanted an answer. But what I told them was, here's the answer I would give you, and here's why I would give it to you. And here are the ways in which this answer is kind of flexible, and here's the way in which this answer is fairly rigid. And so given your problem, your data set that you have that you're trying to analyze, I would do things this way, and this way, and I have good reasons for doing that. And I explained them to them, but really you can tell from the looks of their faces on the Zoom call, they just wanted an answer. They didn't want all the nuance. They didn't care about all the nuance. They just wanted their data analyzed, and they wanted to know what the answer was in the end. So developing nuance in statistics is a challenge. It's something that comes with experience. Hopefully you'll get a feel for that in this class. We'll see how that goes. Single sample t-test. Questions about how you implement it. Yeah.
Just when you're reading the chart, so you use the one tail.
In this case, because it was directional,
Oh, okay.
we're only interested in knowing, is our drug leading to an increase in heart rate that is less than 3? If we were searching for, we want it to hit an increase of 3. It could go over 3 a little bit or be under 3 a little bit because we're looking for it to hit 3, but we're actually interested in, does our drug keep it below 3? In which case, you're not testing for a difference in the positive direction or a difference in the negative direction. You're only interested in differences in the negative direction. Okay? Yeah.
And so, let's say we've done a positive number for our
Oh, you're just done.
T statistic.
Well, it depends on how far the positive was.
No, but I'm saying that not in like this particular instance, but in any instance, we get the positive number.
Oh, it depends on what the question is.
Is that okay? Well, would that be a directional then or no? If it's positive, it would be directional the other way, or it went positive always a two-tail?
No, it depends on whether or not you're wondering if your sample is bigger than the hypothesized value or if it's lower than the hypothesis value. So if your question is directional that way, you're either in the first case, your value is bigger than the hypothesized value, which let me change this to mu. You're only interested in positive values. In this case, you're only interested in negative values. If your hypothesis is just that it's different, then you would be interested in either positive or negative values.
Right, and then the positive or negative on the statistic would say to which direction it's different.
Yes. Yep. So you could say it is different, and it's different in this direction.
Right. Well, so let's say we're testing in that case, we use two.
That would be a two-tailed test. Yep. So you would go to the two-tailed value for 0.05. Yep. Exactly. The two-tailed, one-tailed thing is confusing. I recognize it'll just take you a little while to get used to it. But anytime you see a hypothesis stated this way, this is one-tailed. Anytime you're testing the hypothesis of inequality, you don't care which direction the inequality is, that's a two-tailed test. All right. So anyway, that's the end of that. All right. This is I forgot. Stocks. I have the information in the question itself. You are a stock analyst and you're trying to sell people stocks, and so you are trying to sell a person on a particular portfolio, and they're like, well, how is that portfolio performing? And so you're like, oh, it performs great. It's awesome, super awesome. And the person is like, okay, prove it to me. So you go and you select 10 randomly selected stocks from this portfolio, and this is the percentage change over the course of a year. And the person, of course, wants to know, is the percent change positive, right? Correct. So are you looking for a percent change of 0? No, you don't want that. Are you looking for a negative change? No, you don't want that. You're looking for a positive change. Would this be a one-tailed test or a two-tailed test? It'd be a one-tailed test because you're looking for positive change. Your hypothesis is that the sample that you have is going to be bigger than a hypothesized value of 0 or a percent change of 0. So goes to his portfolio, pulls out these 10 stocks. This is percent change. Conduct a t-test on these data. Somebody check my math. What's the answer you got here? Is this what you guys got? Yeah, oh yeah, negative. So once you finish all the calculations, you have an average change in these stocks of a decrease of 16.8. But if you're trying to sell the stock to somebody, what do you want that difference to be? You want it to be positive, so that when you compare that to a change of 0, which would be basically you put your money into stocks and you expect to get nothing more out of your stocks than you put in, which is bad if you're a stock person. You're testing against something greater than that. So you want this whole thing to be in the positive direction. You want your t-statistic to be somewhere out here. Not only is this t-statistic not out here, it is way the freak over here. So these are, not only are they not different from a change of 0, they're actually different from a change of 0 because the t-critical value is on the negative side, negative 1.833. These aren't not just not increasing, they are significantly decreasing in value. So once again, the interpretation of this is that, 1, you can reject the hypothesis that these stocks are increasing because they're not significantly different from an increase of 0. But even worse than that, they are not increasing because they are actually significantly decreasing. The change in the stocks is significantly different from 0, but on this case, on the negative side. Do you want to be buying stocks from the stockbroker? No, you want to avoid this stockbroker like the plague. This stockbroker is driving a Yugo and showing up at work in suits that he got at the thrift store because he's not making any money for himself or for you. So directionality matters. And when it does matter, you use type 1 tests rather than type 2 tests. We could have easily designed examples for you to look at to look at two-tailed tests rather than one-tailed tests, but these two examples just happen to be one-tailed tests. We'll cover 2 sample tests on Monday, and have a good weekend.